Hello students, now we are going to discuss very important topic, that is soda lime decarboxylation reactions. Soda lime decarboxylation reaction is a very important name reaction shown by sodium salt of carboxylic acid. Sodium salt of carboxylic acid when heated in presence of soda lime. So this is called soda lime. Soda lime. Soda lime is a mixture of sodium hydroxide and calcium oxide. This mixture is called soda lime. When the mixture of sodium salt of carboxylic acid gets heated in presence of soda lime, then it produces alkane and sodium carbonate. Here if you see the reaction, give taken one example, that sodium salt of carboxylic acid when heated in presence of soda lime produce alkane. This is alkane, formula of alkane, and produce sodium carbonate. Here what happens, this carbon dioxide is lost from sodium salt of carboxylic acid and produce RH. Here what happens, as the loss of CO2 takes place, that's what is called decarboxylation. It is called decarboxylation. Loss of carbon dioxide from sodium salt of carboxylic acid due to the presence of sodium hydroxide and calcium oxide. Let us discuss what is the mechanism of these soda lime reactions, decarboxylation reactions. Here if you see the mechanism, here what happens, you take the sodium salt of carboxylic acid, let it is R C double bond O O N A. This is sodium salt of carboxylic acid. First it dissociates, produce R C double bond O minus plus Na plus, produce sodium cation and carboxylate anion. This is called carboxylate anion. This carboxylate anion, what happens, it is losing what, carbon dioxide. If you see the main step, first this minus charge, oxygen carrying minus charge delocalize towards carbon, and simultaneously loss of R minus. This electron move towards carbon, and this, as carbon valence is 4, so carbon forms double bond with this, then loss of R minus takes place. So this is R minus and carbon dioxide is released, loss of carbon dioxide. Here what happens, this R minus, this is called carbanion. It is called carbanion ion, and the percentage of product depends upon the stability of carbanion ion. If carbanion is more stable, the amount of product of alkane will be more. Then this is the called rate determining step, that is slow step. You can say it is a slow step. We have to remember the mechanism. Loss of carbon dioxide from carboxylate ion is the rate determining step, that is slowest step. This is very important. This is the step 1. You can say this is the step 1. After dissociation of sodium carboxylate produce carboxylate ion. This carboxylate ion in the slowest step producing carbanion ion which is stable. Then what happens in the second step, this carbanion ion reacts with water, losing RH, then OH minus. This RH is alkane. This is your alkane. So alkane is produced. Then this carbon dioxide produced in the first step. This carbon dioxide, if you see the reaction, reacts with sodium hydroxide forming sodium carbonate. So ultimately the product is sodium carbonate in the main reactions with the formation of alkane. So this is the mechanism of soda lime decarboxylation. The reaction mainly takes place in presence of soda lime, that is sodium hydroxide and calcium oxide. Here you see what is the role of calcium oxide. Here calcium oxide, it helps to fuse the sodium hydroxide. It helps to fuse the sodium hydroxide during heating. Heating is necessary. Without heating you can't get alkane. During heating, calcium oxide decreases the melting point of sodium hydroxide. So sodium hydroxide, after melting, it completely fuses with sodium salt of carboxylic acid and it forming alkane. So if you see the mechanism, this H is produced from ROH, that means from base, mainly it is produced from base. This H, due to the formation of base and due to the reaction of NaOH with sodium salt of carboxylates, it produces alkane. Okay, so this is the mechanism. Let us discuss what are the different examples, different application of soda lime decarboxylations. If you see the mechanism, the main product is your alkane, and the formation of alkane depends upon the stability of carbanion ion. If carbanion is more stable, then the amount of product will be more. It depends upon the stability. Let us see some examples of decarboxylation reactions. Suppose you take sodium benzoate. This is called sodium benzoate. When it is heated in presence of soda lime, I have written in short form SL. When heated in presence of soda lime, it produces benzene plus sodium carbonate. The product is sodium carbonate. Okay, here you see, here in the mechanism, this phenyl carbanion is produced. This phenyl carbanion reacts with water forming benzene. So the product is benzene. Okay, same way the product will form. It depends upon the nature of the reactant. The sodium salt of carboxyl is taken. You see the second example. If you see, let us take different sodium salt of carboxylic acid. So this is your sodium salt of benzoic acid. Then second example, suppose this is A. The second example, this is your sodium salt of this is your, we can say, that is 2-phenyl sodium acetate. 2-phenyl sodium acetate. If you see numbering 1, 2, so 2-phenyl sodium acetate. This is sodium benzoate. This is the second compound. Then another compound, suppose you take like this. Okay, this is second example. This is numbering 1, 2, 3. So 3-phenyl sodium propanoate or sodium propanoic acid. Sodium salt of 3-phenyl sodium salt of 3-phenyl propanoate. Okay, propanoic acid. 3-phenyl propanoic acid derivative, and this is 2-phenyl acetic acid derivative. This is only benzoic acid. If you see the comparison the rate of reactions. If you see the nature of carbanion form, if you see, so this is your phenyl carbanion, your main product is your phenyl carbanion after loss of carbon dioxide. Here the carbanion is, if you see the carbanion, this is your CH2 minus, and this is your, the carbanion mechanism is CH2 minus. But if you see the stability, suppose this is A, this is your B, this is your C. If you see the stability, this is phenyl having, benzene having minus charge is very unstable, and benzyl carbanion is more stable by resonance. This is due to resonance. Delocalization takes place due to the help of phenyl group. Here delocalization is slow because delocalization comparatively is difficult in case of C, but in case of B delocalization is faster. In this case B, the delocalization faster due to resonance. Here delocalization is not takes place, but this phenyl having minus charge is most unstable. That's why, so reactivity order, that C first will be B will be the more reactive carboxylate, then which one? C, then A. Why B will be the more reactive? Because in the reaction, if you see the mechanism, the carbanion is more stable. This carbanion is benzyl carbanion. Benzyl carbanion is stabilized by resonance. That's why B will be the more reactive acid. Then C, then A. In case of A, the that phenyl carbanion is produced, which is very unstable. So the order of reactivity, first B, then C, then A. It depends upon the stability of carbanion produced. So you have to remember, you have to keep in your mind that which carbanion is more stable. If carbanion is more stable, then the parent acid, that salt, will be more reactive towards soda lime decarboxylation. So remember this concept. Okay. Then third example, let us discuss. Here in the third example, if you take three types of acid, I will take here this one, CH3 whole 3 C COONA, then CH3 whole 2 CH, then COONA, then CH3 COONA. Okay, here this is first, this is your second, this is your third. Similarly, if you see the carbanion formation, let us take, this is will be the carbanion part, and here this carbanion, and this is carbanion. Here this carbanion is a tertiary carbanion ion, and this carbanion is secondary carbanion ion, and this is your primary carbanion. We know the stability of carbanion, primary greater than secondary greater than tertiary. So the stability of primary carbanion is more stable, means we can say that C will be more reactive than B than A, because the carbanion stability is more, means the parent salt, parent acid, that will be more reactive towards soda lime decarboxylation. Okay, that's why C is more reactive than B than A. C is your primary carbanion, which is more stable than secondary than tertiary. So this is the order. Okay, then fourth example, if you take fourth example, similarly we can take, it required practice, CCl3 COONA, this is one salt of one acid. Suppose this is A, then CF3COONA, then CH3COONA. This is B, this is C. Here similarly we have to see the stability of carbanion ion. Here which carbanion is produced? This is the carbanion. So this is your carbanion and this is your carbanion ion. Here you see the stability. Here in both case minus I effect takes place. Here 3 chlorine, 3 minus I effect, and 3 fluorine also 3 minus I effect. So stability is more compared to methyl. But here what happens? In case of CCl3, if you see the stability, and here C, F, F and F minus, and here C, H, H, H minus, if you see the structure, and this trichlorocarbanion ion, this trichloromethyl carbanion ion, it is here it is more stable, although it has minus I effect chlorine, but here what happens, pi bonding, d pi bonding is more. Here what happens, if you see the structure, here what happens, here chlorine has your vacant d orbital, and this pi bond, this lone pair negative charge forms a pi bond. Back pi bonding is faster because chlorine has vacant d orbital. That's why it is more stable than trifluoro, then it will be stable than methyl carbanion. So why trichloromethyl carbanion is more stable? Because the chlorine atom has vacant d orbital, it forms d pi p pi bonding with carbon carrying negative charge. So that's why it is more stable than fluorine. But fluorine has no vacant d orbital, that's why delocalization is slow. Although it has minus I effect, but delocalization is faster in case of chlorine. That's why trichloromethyl carbanion is more stable than trifluoro. That's why the acidic character, the decarboxylation faster in case of A, then B, then C. This is the order of reactivity of carboxylic acid, having 3 halo compounds substituted: trichloro acetic acid, trifluoroacetic acid, and acetic acid. So order of reactivity is this order. It depends upon the stability of carbanion. Okay. Then fifth examples. Here what happens, if you see the examples, similar examples we can take, that here this is one unsaturated acid having sodium salt of acid, then another acid you take like this having acid group like this. Okay, here if you see the stability of carbanion ion, in which part carbanion is produced after loss of carbon dioxide, this is your carbanion and here this is your carbanion ion. Here if you see the stability, in the first case A and V, if you see the delocalization, this carbanion will be easily delocalized by resonance compared to this one. Here delocalization is stopped at this point. Here delocalization is not possible. That's why this is less stable. So as A produce more stable carbanion ion compared to B, that's why acid A is more reactive than acid B towards soda lime decarboxylation. Okay. In this type of question, generally it will be asked in your competitive examination. So you have to think which carbanion is more stable. The carbanion is more stable means the parent acid, its salt will be easily decarboxylated by soda lime test. So you have to think the stability of carbanion. Okay, then sixth number question, if you take similar example, if you take next example, let us take this acid. Okay, then second acid is like this, and third acid is like this. If you see the stability here, if you see the stability, and this is your carbanion produced at this point, here carbanion will produce at this point after decarboxylation, this point. So what is the stability here? This, you see the stability is not possible, delocalization is not possible. Here delocalization is possible by resonance. Here also delocalization is faster because the benzene like structure will form after delocation. So this is A, this is B, this is T. Here what happens? This carbanion is more stable compared to second one. So C will be more active than B than A. Because in case of C, this acid delocalization is faster. Because benzene ring will be formed. Benzene ring having 3 pi bond easily delocalized by resonance. That's why C, the parent acid, salt of parent acid will be more active than B than compared to A. Here in case of B, one delocalization takes place, but here the complete delocalization takes place due to alternate double bond, single bond in the ring of a benzene ring. That's why C is more reactive than B than A. Then come to another example, that if you take this example, the example like this, C has 3, C has 2, C double bond O, O and A, this. Then second example, if you take C has 2, double bond CH, then COO-Na. Third example, CH triple bond C, then COO-Na. Then CH3 COO-Na. A, V, C and D, 3 types of acid derivative if you see. But if you see the stability, here what happens? If you see the stability of carbanion ion, here this minus charge will be produced here, and here this is the minus charge, this is the minus charge, and this is the minus charge. If you see the, here the hybridization is sp3, here hybridization is sp2, here hybridization is sp, here hybridization is sp3. But if you see order of stability, and as sp carbon has more S character, sp carbon has more character, S character, so electronegativity of that carbon is more compared to sp2 and sp3. sp carbon is more electronegative than sp2 than sp3, so the carbanion automatically will be more stable. So as C is this, the carbon having negative charge, having triple bond, that carbanion will be more stable. So the order of reactivity will be C, then will be B, then will be D, then will be A. Why D? In case of D, what happens? Methyl carbanion is produced. In case of A, ethyl carbanion is produced. Ethyl carbanion is less stable due to plus I effect. It has plus I effect. Which one? This is your plus I effect due to methyl group. In case of CH3, CH2 minus, it has plus I effect. So it is less stable compared to methyl. That's why the order of reactivity is first C, because it has triple bond carbon, then B, that it has double bond carbon, then D, because D is only free methyl carbon, then A having, that is ethyl group, which has plus effect, it decreases the stability of carbon ion. Plus I effect decreases the stability in compared to methyl. That's why the order of acidic character is C, then B, then D, then A. Okay. Then question number 8. Question number 8 is like this. What is that? You take this acid derivative. Okay, this is the acid. If you do soda lime test, and on heating, result will be benzene. Your result will be also benzene. Loss of this produce benzene group. Okay. If you see another example, let us take this example. Okay. Here suppose one bromine is here and this is your carboxylate ion. Okay. First soda lime test if you give, and here it is bromine. If you see the mechanism, okay, this produce, and this is your minus charge after loss of CO in the first step, formation of carbanion ion. If you see this carbanion ion, what happens? Delocalize this negative charge to this, loss of bromide Br minus, because this carbon is more polar. Carbon attached to bromine is more polar. That's why negative charge attack to the carbon attached to bromine. So the product will be this product. This is your product. One bicyclic compound will form. Bicyclic compound will be formed in this way due to loss of Br minus and attacking of the negative charge towards the carbon having Br minus. Okay, so this is also one important product, decarboxylation reaction. Similarly, if you take another example, this is also important example for this case, similar type. If you take CH3, CH, Br, then CH2, COONA. Similarly, first step, the carbanion is like this, CH3, CH, Br, then CH2 minus. As per the mechanism, the first step is the formation of carbanion, and this carbanion, what happens? It will be the negative charge delocalized in this case. So the formation of one alkene. This alkene is also stabilized by hyperconjugation. It has 3 hyperconjugation, that's why it is more stable. So this product, this reactant, this compound, when it reacts with the soda lime, it produce propene. The product is propene. Because the formation of a carbanion ion, this carbanion ion delocalize the negative charge with the loss of bromide ion and forming double bond. So propene will be formed. If you take another example, this is also very important examples. If you take like this, here if the product is like this, if you compare, this is the negative charge, this is your, take like this, the bigger compound, take like this, then COONA, then which one? Like this, COONA, which will be more reactive. Here if you see the mechanism, here what happens? This is your minus charge and this is your minus charge. So this minus charge is produced like this and this produces like this. Which is more stable? This is more stable by resonance. As it is more stable, this which one? That cyclopropenyl anion. This is called cyclopropenyl anion is more stable due to delocalization compared to cyclopropyl anion. That's why the parent acid, if you see, this is A and this is your B, So A is more reactive than B. Okay. Similarly, I will take this another examples. If you see the, suppose this is your compound, carbonyl group is here, and this is your carboxylate ion. Then another compound is, if you see, this is your carbonyl group and carboxylate ion. You will see here what happens. Two carboxylate group is here. This is your carbonyl group, this is your carbonyl group, and this is the one carbonyl group. So the minus charge produced here and produced here. Here only one carbonyl group, it is two carbonyl group. Carbonyl group is a minus I affecting group. That's why double 2 minus I group is attached to carbon minus. That's why this is more stable. That's why A and B, if you take, so A is more reactive than B, because the carbanion produced in the first compound, it is attached to two carbonyl groups, more minus I effect. So carbanion is more stable. That's why the parent compound A is more reactive than B. So today we discuss different types of product by soda lime decarboxylations and the comparison of reactivity of different carboxylic acid, different salt of carboxylic acids. Only the main principle, main theory is the stability of carbanion. If stability of carbanion is more, then the compound will be more reactive. Okay. And the mechanism, the first step, the formation of carbanion is the rate determining step, that is slowest step. That's why the stability of carbanion ion gives the result of alkane. In both cases alkane is formed, but some cases rearrangement also takes place. We have discussed this example also. You see here alkene is produced instead of alkane because delocalization, because these are deals. So depends upon the nature of carbanion produced and its stability. So in this case, in this topic we discussed so many examples of soda lime decarboxylation. So I hope you understood these videos, the mechanism and different application of soda lime decarboxylation reaction. If you like this video, please share this video to your friends. And if you have not subscribed my channel, that is Chemistry Goal, please subscribe it and share this video to your friends. Okay, thank you all.